go. So, welcome to class, everybody. I'm your professor. I'm a pretty cool guy if you hang out with me after class. But I'm also cool in class, which is what makes me different from other teachers. You're going to love it. It's going to be great, alright? So for today, we're going to review like the equations you covered in the chapter on relative velocity and relative acceleration, focusing more on relative velocity. Basically all that is what is the velocity of one point on a body with respect to another point on the body. And I'll explain that in a second. So our objectives for today's lecture, number one, is to review the relative motion equations. And for shorthand, I'm just going to write them up here. So velocity at point B is equal to velocity at A plus the angular velocity of the body cross the position vector from one to the other. Okay, that's one thing for the velocity. And then for acceleration, the equation is basically just the time derivative of this. You take the derivative of this equation, and you can get what the relative acceleration should be. And this is again all in the books. I'm not going to go through the derivation of it. What I want to cover today is for you guys to be able to see what the equations are saying and see what they're doing. Okay, so then it's going to become the acceleration of A plus the angular acceleration of the body cross the position vector 2b from A minus the angular velocity of the body times the position vector 2b from A. Okay, so that's one objective of today's course, of today's lecture. The second objective is for us to review the instantaneous center of zero velocity method. This is another method. It's like a quick and dirty way to figure out the angular velocity of a body or to figure out the velocity at any point on it. So we're going to call it, so we're going to review the instantaneous center method. Okay. So these are our objectives for today's lecture. You should be able to come away with these 2 points. Okay, so for starters, let's say, so we're talking about relative motion equations. Let's say we're looking at, I don't know, a floating potato in the middle of space. This is our magical potato, and it's instrumental for most engineering applications. So we've got on this magic potato a coordinate axis, Z, Y, and X, so we can get an idea of where the potato is oriented. Okay. If we're looking at 2 points of the potato, point A and point B, okay, what basically end up finding is if I were to draw vectors from the origin of interest to these different points, this would be the position of A, and this is the position of B. Okay? By vector addition, right, what I can get is, if I want to get 2B from A, this would be my vector, right? And this is, we'll call this vector, we'll call this position vector RB to A. So, if I were to use vector addition to find what the position is of B, let's say all I know is the position of A, and I can measure from geometry whatever the position of this vector from A to B. Basically, what ends up happening is that the position vector to B is equal to the position vector to A plus this relative position from A to B, or 2B from A. Okay. If I take the time derivative of this, so basically take this the derivative d by dt of this whole expression, I get that r sub b dot equals r sub a dot plus r sub b to a dot. These dots indicate that it's a time derivative, so I can replace this with the velocity at B equals the velocity at A plus the velocity of B with respect to A. Okay? This is awfully familiar to this equation here. Velocity of B equals the velocity of A plus, but the difference is in this expression here, this omega cross R, where here I wrote it as V from B to A. Okay? If these 2 points lie on the same body, this expression can basically be rewritten as assuming that the body has some angular velocity, omega, this expression can basically then be rewritten as the omega of the body cross the position vector from B to A. Okay? So this is how we get our relative velocity equation. So basically, what you're just saying is that it starts from the difference in the position vectors here, and then you differentiate it to get an expression that results, basically it's the difference in the velocities. So when someone says relative velocity, what they're basically saying is, what is the difference between the velocity of one point versus another point? Or another way to phrase it, what people say is, if I'm standing at point A, or point O here at the origin, what does the velocity of A look like? Okay, and that's just described as VA. Now if I were to shift where I'm standing, and I'm standing at point A, what is the velocity of B going to look at from a person standing at A? So there are two different ways to understand what relative velocity is actually saying. Okay, so this is the basis of our equation here. This is the general form. Plus omega plus R2B from A. And like I said again, in the textbook, it goes over the actual derivation for this equation and how this omega cross R comes from. And also covers if you were to take the time derivative of this expression, so if I go d by dt of my general equation here, I then end up with this awesome acceleration expression. Acceleration of B plus acceleration of A plus alpha, which is angular acceleration of the body, cross R2B from A, minus omega squared R2B from A. Okay? So these are two expressions we want to hold on to. Keep them in your pocket because they are importante for the example problem we're going to go over later. Okay? So, Barbara, I have a question for you. Let's say I have two positions on the body, C and D. Okay? And how would I, if I know the velocity at D, right? So I know VD, okay? And we know this omega. Can you, how would I find the velocity at this point C? What would that equation look like?
With respect to origin, you mean?
Yes, with respect, so I'm trying to find the velocity with respect to the origin here, okay?
So the same method that you did there. So VC will be VD plus VCD.
Okay, and for this case, what is VCD going to be?
Omega R CD.
Yep, omega times R 2C from D. Perfect. That's basically the gist of it, and it's really straightforward and simple. The other method I wanted to show for you all, and I'll try to mark off the territory, is something known as the Instantaneous Center of zero velocity. So what it's basically saying is this. If you look at this Idaho potato, right, we call this our origin, and what we're assuming is that at this point, the whole body is rotating about that point. We're going to label it O. So what we're saying is since this point is fixed in space, it's like a hinge, it has zero velocity, okay? So I'll redraw it over here so it's a little easier to see. This is our magic potato. Here's the axis, right? So we're saying that this point's not moving, all right? So if I look at a velocity here, like we covered in the textbook, is if you draw a line from the point about which a body is rotating to the point in question, the velocity is always going to be tangent, or perpendicular to this line here, which connects the origin and the point of no motion to the point in question. So that applies for any and every point that I'll happen to look at on the body. We're assuming that angular velocity is going this way. So I draw a line here. The velocity at that point is there, perpendicular. I draw the line here. Therefore, the velocity has to be kablamo, perpendicular, and again. Okay? So basically what we find is if you want to know, if you have just the velocities of 2 points on a body, but you don't have like the angular velocity, you don't know where the center of rotation is, You can find it by just connecting where these perpendicular lines intersect. So what we're going to do now is look at another magic potato, but we don't have an axis. All we have is this point, and for some reason we know that its velocity is going this way. So the velocity, I'll say, of point C. And we have this point, whose velocity we know is going this way, V sub D. Okay? So if I were to find the instantaneous center, like the point about which this body is actually rotating, I'm simply going to draw a line perpendicular to this velocity vector, and a line perpendicular to this one. And this right here becomes our instantaneous center of zero velocity. So basically, as the name suggests, at this instant in time, that's the point on the body that has zero velocity, but it's only instantaneous. So if I were to look at the whole velocity of the body a second later, that I see is going to change position. So since we're only we're like taking freeze frames in time, this is what we're looking at, okay? What's nifty about this is, fortunately, if I just know the directions of the velocities, right? And let's say all I have is the directions of them. I do know also that I have an angular velocity omega. Like we discussed earlier, I didn't actually discuss, but like the book covers, the velocity of a point from the point of rotation is always just going to be, the velocity is always given as omega cross r, where r is the distance from the point of rotation to the point in question, okay? So in this case, we'll call this distance here r1, and this distance here r2. So to find VC, I simply go, oh, okay, I know omega, and that's going to be cross r1, and bam. I now know the velocity at C. And so Steve, what would the velocity at D be then?
If you follow the same method, V sub D equals omega cross R2.
Okay. Straightforward, yeah? So these are the two principles these objectives I want you to come away with lecture from today is the relative velocity equations and the instantaneous center. I'll go now for an example, which is trying to give you guys an idea of when to use one over the other. But Babak, if you could explain to me, what is this equation saying, this relative velocity equation, if you were to break it down term by term, what is it saying to us?
So it's saying that the velocity at point B
Yeah.
is equal to velocity at point A plus the angular velocity times the arm length from A to B.
Okay, so again, if I were to say, all right, I have the velocity at C, now find for me the velocity at the point B, what sort of process would you go through, mental steps?
So I'll find the velocity of C with respect to the origin, O, and then I add the relative velocity, that's the angular velocity of the whole body,
Yep.
across the arm length.
Simple as, right? So that's the general gist of it, okay? So what we're going to do now is go over an example problem. How much time have we got?
You have a minute and a half left.
I've been 19 minutes?
Oh, no, sorry, up to 15 minutes.
Okay. All right, so now I'm going to erase everything, and we're going to go over an example problem. Gentlemen, how do you guys feel about this angular velocity stuff, relative velocity? Does it make sense?
Makes sense.
Okay, cool. I'm going to test it. I'm going to test how much sense it makes. So you have an example problem where we've got this disk. Okay? It's rolling on the ground. However, it's connected, it's hinged. Let's get this here. It's hinged, so this is the little cross section of the disk. It's hinged here to an arm, which is hinged here on a slider. Okay? We'll call this point B. We'll call this point A. We know the distance between here and here is 1 meter. Right? It's currently having an angle, different color, of 30 degrees with the horizontal there. And it's got a radius of 0.4 feet. or meters. I keep everything in meters. I like metric system. And it's got an angular velocity at this moment of omega equals 1.6 radians per second. Is what we're dealing with. Okay? And the distance from here to here is 0.2 meters. Okay? So what I want us to find is to calculate the angular velocity of the bar AB and the velocity of the slider B when the mechanism is at this position shown. Okay? So basically what we're trying to find is, if I were to isolate these things over here, this is AB. We want to find the angular velocity of AB, and we want to also find the velocity of the point of B. Alright? So what things do we know? We know the angular velocity of this disk, right? Is the first thing we know, okay? So, I can show you two ways to solve this problem using the two methods we talked about. One using the instantaneous center velocity, the other one using the relative velocity equations. We'll go relative velocity because those are more regimented, more structured for right now. Okay? So remember, like we said, the first thing you know is you have to ask yourself, okay, if I need to find the velocity of this bar, like the angular velocity of it, then what equation can I use that will give me some instruction on that? Bam, our relative motion equation, right? So we said that, okay, in order for it to work, I need VB equals VA plus omega of the bar AB cross R. What don't I know? Well, I don't really know VB, except that I know it's confined to move up and down. So it's confined in the J plane. So let me just put that down here. We're going to go with the J and I hat convention. Okay? So I don't really know all of VB. All I know is that it has no horizontal component because it's confined to move in the slider. And I know it's got some vertical component. I just call it V sub D in the Y direction. Okay? VA, similarly, I don't know anything about right now because I just know that it's connected to the slider. It's also connected to this disk. So all I have is, so this is another question mark. I got VA in the X, VA in the Y. Omega AB is given. Actually no, omega AB also we don't know. Ooh, it's going to be kind of tricky. We don't know nothing. However, R from A to B, or from B to A rather, we do know. We can find just from the geometry. They give the length, they give the angle. That can be found. So we don't have either of these expressions, okay? For VB, we kind of simplified it, but we know we still can't move forward because we need the rest of this equation. Okay? This would be, omega AB, we're going to assume to be in the k-hat direction. Cross. And then this is known, and this is known, just from the geometry. The position in the x and y coordinate. Alright? However, so it looks like if we can find, so this equation is one equation. We have 1, 2, 3, 4 unknowns currently. Okay? So let's try to take a step back and see, is there any way we can find more about any of the terms of this equation? VB, we can't really. Omega AB depends on these other terms. So let's try to isolate V sub A. Because VA is a shared point between the arm and the disk. Right? So what we find is, okay, so we can use VA also for this disk, which we know the angular velocity for. Maybe if we can find the velocity of one other point on this body, then knowing omega, we should be able to find the velocity then at A. You guys follow me? Okay. So another condition is that the disk is not slipping on the ground, which means that the disk and the ground at that point share the same velocity, otherwise they'd be slipping against each other. So we'll call this point O for reference sake. So if I wanted to find the velocity at A, knowing that the velocity at O is 0, and that the angular velocity of the disk is this omega here, I then use this same equation, but for these 2 points. So I'm going to get that the V at A should be equal to V at O plus omega of the body cross R to A from O. Right, guys? This we know is 0. Ka-ching. this is given, this we can find, and we can find piece of A. Pretty good, right? Alright. So let me keep with the blue. VA in the X is going to equal, so if we break it down to vector form, and VA in the Y is going to equal, this is 0, 0, plus this is 1.6 radians per second in the k-hat direction, cross, and then the position vector from O to A, this is R, is simply going to be, we'll call this angle phi for now. I'm not going to solve it completely, but just give you guys an idea. Okay? You're going to get, actually it's easier than that. We know from O to A, actually you don't even need the angle. It's much easier because this length is given and we know the radius of the disk. Alright? So in the X direction, it's simply going to be minus 0.2 meters, and then in the Y direction, it'll be positive 0.4 meters. Okay? Do all that, you ultimately get that VA is going to equal, let's see here, VA in the X and VA in the Y. It's going to equal 0.64 a hat and 0.32 j hat. Okay? So we simply take this solution, throw it into here. Go back a step. And we get 0, V sub B in the Y is equal to 0.64 I hat and 0.32 j hat, plus the unknown omega AB in the k hat direction, cross, again, the known position vector from A to B. I don't want to write it, I don't want to confuse you guys for now. Okay? So now what do we have? Two equations, one in the X direction and one in the Y, and two unknowns, omega AB and VB sub Y. So the two equations and two unknowns, the problem becomes solvable, and we ultimately yield that. I'm just going to jump to the conclusion. Ultimately, this yields, when you do the math, you guys, I need for you to do that after class yourself, but you ultimately will get that omega AB is equal to minus 1.28 radians per second, so that's clockwise, and the velocity of B in the Y is equal to minus 0.789 meters per second. Okay? Cool. Another quick and dirty method to solve this problem using the instantaneous center of zero velocity would be looking at the setup, the disk, the arm, connected to the slider. I know that the velocity at B is confined to move in this direction. So VB. Okay? And I know that given that the instantaneous center of zero is here for the disk, the velocity at A, therefore, if you were to connect the two, this being at point A, would have to be in this direction. Alright? You can find the instantaneous center of zero velocity by drawing lines perpendicular to their velocities. Bam. That becomes our IC. Then by just using geometry of the problem, if you can find this length and you can find this length, then it becomes possible to go ahead and finish solving it. But that's it in a nutshell, guys. We covered relative motion and instantaneous centers. I think you guys are experts now. Any questions? Yes, Steve.
When you did that, when you did that instantaneous center method, the instantaneous center is outside both of the bodies. Is that okay? Can that happen?
That's perfectly okay, because like I was mentioning before, the IC doesn't have to be on the body. It's just, if you were to picture it, this is at this instant, it's like as though this whole body is rotating about that point. Okay, so the IC doesn't actually have to be on the body. It's just a representation to show you, like physically, what you're seeing then is if, let's say this marker were the bar, at this instant, it's as though the bar is rotating about the point C. Okay, so it doesn't have to be on the body now. Any other questions? Bazinga. We're done. Cut the tape.